Thank you so much for the invitation to speak at Berkeley. And I'm going to be talking about some recent work with Jonah Cudliffe-Lamb, Hassan Chapurian, and Hong Liu. OK, so I want to start with two kinds of motivations for this work. The first one just comes from wanting to understand, in general, the dynamics of chaotic quantum many-body systems, and in particular, the question of how thermalized states behave in such systems. So suppose we have a chaotic quantum many-body system, which is initially in a pure state psi 0. Then at late times, we expect that the system thermalizes, which means that details of this initial state should be forgotten. And if you consider macroscopic properties of the time-evolved state psi of t, which, for instance, can be obtained by acting with some unitary time evolution operator on psi 0, then those should be possible to approximate by using this equilibrium density matrix rho equilibrium. Okay, so this means in particular that if I look at expectation values of some few body observables in psi of t, then those should be quite close to their values in rho equilibrium. For instance, this could be the canonical density matrix. But to learn more about the properties of this thermalized state, we can go beyond things like expectation values of few body observables, and we can ask how information theoretic quantities such as entanglement entropy behave in this state. But this gets a bit tricky because in general, the unitarity of quantum mechanics means that this state psi of t is a pure state, and the values of quantities like entanglement entropy in all regions in this pure state can't be equal to those in rho equilibrium. So in particular, this psi of t should satisfy the property that the entanglement entropy in any region A is equal to that in the complement. But that is not true for a state like rho equilibrium. So we can then ask the question in any quantum many-body system of whether we can express quantum information theoretic measures in psi of t still in terms of some parameters of rho equilibrium. And this would mean, so the reason why this would be very convenient is that in general, this psi of t contains like a very large number of parameters in a many-body system. It's very hard to compute. But if we had some description in terms of rho equilibrium, it could become easy to compute. And it could have some universal properties which depend only on things like the temperature or the chemical potential. So if we can do this, then a natural question would be, what is the resulting universal behavior of information theoretic quantities in such thermalized states? Okay. A second set of motivations comes from wanting to understand the dynamics of black holes. So in recent years, there has been strong support that black holes can be treated as an example of strongly chaotic quantum many-body systems. In particular, the process of the formation and evaporation of a black hole can be seen as an example of this general process of thermalization that I mentioned. Concretely, if you imagine starting with an isolated star in some pure state psi 0, and it undergoes its gravitational dynamics and forms a black hole, then at late times, it was observed by Hawking that this black hole actually emits some thermal radiation. And this thermal radiation seems to know very little about the details of this initial state. Okay? So because black holes are an example of general chaotic many-body systems, we can try to use universal properties of such systems in order to make predictions about black holes. And then by trying to verify such predictions, we can confirm that black holes obey the usual rules of quantum mechanics. Or if it turns out to be difficult to verify them, and we have to do it in some non-trivial way, then we could potentially discover some new features of quantum gravity. Okay? So one example of this general logic, which I'm sure that everyone here is somewhat familiar with, is the derivation and verification of the Page curve. Okay? So Page used a very simple model for a state that comes from a highly chaotic time evolution. He just assumed that it behaves like a random pure state. And you can only consider such random pure states in a finite dimensional Hilbert space. So that's what he did. And then he considered the average entanglement entropy of such states in some subsystem A. And this turned out to have a very simple dependence on the dimensions of A and its complement. And it just turns out to be that the entanglement entropy of A is equal to that of A bar, and both are equal to the minimum of the log of dA and log of dA bar. Okay? So now if we assume that black holes produce at late times some complicated state which is similar to a random pure state in the total Hilbert space of the black hole and radiation, then based on this formula, because we know roughly that the dimension of the black hole is sort of decreasing along this blue curve during the evaporation process. The dimension of the radiation is roughly increasing along this red curve. You can make a prediction that the evolution of both the entanglement entropy of the black hole and the radiation should be the minimum of these two curves, which is the solid curve in this diagram. Okay, and in particular, it doesn't keep increasing for all times and turns around at the page time. And you can also ask other questions by using the same model for the state created by the black hole dynamics. So for instance, you can ask, if you throw some information into the black hole initially, then at what point does it start to come out in the radiation? And this was done by Hayden and Preskill, again by using random pure states. And they found that the answer to this question is also that the information starts to come out at the same time when this entropy curve turns from increasing to decreasing. So that also happens at the page time. Okay? But of course, a calculation in semi-classical gravity by Hawking seemed to predict that black holes violate the unitarity of quantum mechanics, and the entanglement entropy of the radiation keeps increasing throughout the process. So, so in order to verify the page curve, this required some non-trivial calculations, and it was recently verified by using a semi-classical gravity approach by these authors. But this approach involved certain new features of semi-classical gravity, such as islands and replica wormholes. So this calculation that they did had both of these features that I mentioned in the beginning. So it verified that black holes obey the usual rules of quantum mechanics, but it also, in the process, taught us about some new features of gravity, which were these islands and replica wormholes. Okay? But now we can ask more questions in the same spirit about the entanglement structure of the black hole and information recovery. And in order to do this, we can use quantities that go beyond entanglement entropy. So in particular, we can use the logarithmic negativity, and we can also use, to understand the process of information recovery better, a quantity called the Petz map fidelity. And I'll explain much more as we go on what these quantities mean and why we should study them. But in principle, this allows us to probe the black hole dynamics beyond just using entanglement entropy. And another sort of simplifying feature of this calculation by Page was that he used random pure states, which can be seen as a model for equilibrated pure states at infinite temperature. But in any situation where you want to take into account the effective energy constraints, you need to consider finite temperature. And whenever you have a quantum field theory, you don't have an infinite dimensional Hilbert space, so you have to consider finite temperature. Okay? So we want to be able to ask these questions in setups beyond just random pure states. Yeah, so what we did in these papers, and what I'll discuss in this talk, is this method called the equilibrium approximation, which we developed in this earlier paper from a couple of years ago, which addresses these two general questions about quantum many-body systems that I mentioned on the previous slide. So it allows us to express information theoretic measures in finite temperature equilibrated pure states, and to do so in a way that is entirely in terms of equilibrium quantities, like properties of this density matrix rho equilibrium, but to still do it in a way that is consistent with unitarity. Okay? And yeah, and then as expected, this method ends up being just in terms of the equilibrium density matrix, involves a small number of parameters, and it turns out to be efficiently computable. So you can actually study the properties that these quantities will have in a variety of universality classes of thermalized states. Okay, and then so this paper was originally in the context of entanglement entropy, and we actually explained how to systematically derive the replica wormhole prescriptions as an example of using this method in general quantum many-body systems. But what I'll talk about today is how if you apply this method to logarithmic negativity and Petz map fidelity, then you find some surprising features of chaotic quantum many-body systems at finite temperature. And when you apply these predictions to the black hole context, then this gives some potentially even more surprising predictions for the dynamics of evaporating black holes. Okay? Yeah. So that was the sort of general background for what I'm going to do. Are there any questions at this point?
Are you going to tell us what logarithmic negativity and Petz map fidelity?
Yes, absolutely. Yeah. So this is just to tell you, these are some quantities for now beyond entanglement entropy which probe questions about, like logarithmic negativity probes some features of mixed state entanglement, and path map fidelity probes some more fine-grained things about the information recovery process. Okay, great. Okay, so yeah, so the plan will be that I'll first describe the setup and method that I use for studying entanglement structure, and then I'll present the results for entanglement structure that we found and the applications to black holes, and then I'll discuss the results for information transfer. Okay, good. So for probing the entanglement structure, the setup that we used was just, again, consider that we have a general chaotic system and a thermalized pure state psi of t. So this is thermalized in the sense that it's been evolved to late times, and you expect that if you look at few body observables, they would have thermal expectation values. So now for this state, you can ask, what if you divide it into 3 parts, and you want to ask how correlated are 2 of these parts, which you can call A1 and A2. So now the state on, even though the state on the whole system is pure, the state on A1, A2 by itself is a mixed state. And this means that we're going to have to understand entanglement in mixed states. So in general, the question of bipartite entanglement in pure states is pretty well understood at this point, and it's captured almost entirely by the entanglement entropy. But mixed state entanglement has a much richer structure, and it involves a variety of inequivalent quantities. And it's much less understood, especially in the context of many body systems. So 2 useful quantities for probing the entanglement in mixed states are the mutual information and logarithmic negativity. Yeah, I'll explain the differences between these quantities as we go on. But it'll turn out that they capture some different aspects of the entanglement. So what we'll do in this setup is that we'll vary the relative sizes of these 3 subsystems, A1, A2, and B. And we'll use the equilibrium approximation method to find both the mutual information and the negativity between A1 and A2. And as we vary the sizes, we'll see some qualitative changes in the forms of both of these quantities. And these qualitative changes can be seen as entanglement phase transitions. Okay? So this was in the context of general many-body systems. When we specialize to the black hole case, we'll think of A1 and A2 as being the radiation divided into 2 parts, and B as being the remaining black hole. Or at least that would be the most interesting case. Yeah?
I should have maybe asked this earlier, but when you gave the example on your very first slide about the phenomenon entropy of a subsystem,
Yeah.
Well, we know that it's equal to that of the equilibrium state so long as you look at less than half.
Right.
After that, it's not.
Yeah.
We could have switched to the complement and try to sort of check it that way. And I'm trying to understand what I mean, the same will be true for things like the mutual information here, right?
Yeah, the mutual information.
If you are very small, then it's going to look like it'll be the same as in the equilibrium system, and once they are together pretty big, then I guess it's...
Yeah, you get some, that's essentially why on varying these different sizes, you get 3 different forms of the mutual information. But the logarithmic negativity turns out to be a little more non-trivial.
So the point here is not that you're introducing, what's the punchline going to be? That we should look at just, so we should also forget about the mutual information the same way we're going to forget about the phenomenon entropy, and for the same reason? Or?
No, actually we shouldn't forget about the mutual information, because the mutual information will tell us something interesting. It'll give us a good way of contrasting the results that we eventually find in terms of negativity with the usual understanding of these things.
Because, so the goal here is, the rules are not that you're interested in something which will always give the same answer as for the equilibrium state. Because that's not what you're looking for.
Well,
because
we don't.
Either the mutual information or the phenomenon entropy of a subsystem would satisfy that criteria.
Is it true that you are trying to just have a mixed state, like a thermal state? You have only that information. But assume that this is not the true state, but it's a late time of some pure state, which is unitary. Then how come you can get information about quantum information quantity, which is applicable to pure state just from this raw information? Assuming unitary.
Yeah, so.
Then of course, for
Then it has some non-trivial mutual information. Yeah.
And then you say that that's the true answer for a pure state, although you're using information only.
Exactly.
Temperature. And
Yeah.
you want to do similar thing for other quantities.
Yeah, exactly. Does that make sense? So, so for the mutual information, okay, so by the same point that you mentioned about the entanglement entropy before, if you take this A1 plus A2 to be less than half of the system, then you expect that the state will look roughly thermal, and so you should have basically no mutual information between these two regions. Yeah, and then you get essentially two kinds of non-trivial structures, which you can see from this equilibrium approximation method. For the case where A is bigger than half of the system, you get some non-trivial entanglement between these two regions. But the negativity will actually turn out to, but then we apply the same method to the negativity, and that will turn out to give a slightly different picture of what happens as you change the sizes of the systems.
Ultimately, the zero for the goal is to figure out when the state has thermalized, and to do that by somehow comparing some quantities with what they would be in the equilibrium state.
No, the goal is not to figure out when the state is thermalized. So we're assuming that it's an input in this calculation that the state has thermalized. So it's more just to see, after it's thermalized, but it's still a pure state, how do these quantities behave for different choices of the subsystems?
So suppose you have some late time, your state is completely well approximated, very rough level, by a thermal density matrix. But if you compute, for example, entanglement entropy of the region bigger than half, the answer is not right. But we know
by not right. So
because
from what you just said, I would have said, well, so we can do that for a lot of quantities. We can ask about the fundamental entropy, and the answer is going to be that if the state is properly thermalized, it's going to follow the page curve. And maybe what you're going to tell me is now for other quantities, what's the analog of the page curve? Basically.
Sure.
Is that a way to characterize what you're doing?
Yeah, sure.
Okay.
Yeah, I guess you have two parameters that you can vary in this setup.
Yeah, exactly. There's more stuff to vary, and you
Yeah.
can ask more questions.
Yeah. Yeah, exactly.
That's the question. Yeah, what is the difference between A1 and A2? Would you consider that they would have the same dimensions?
Sorry, say it again?
A1 and A2 were considered they have the same size over space?
Not necessarily. So we can vary the relative sizes of A1 and A2 and of A relative to the whole system. Yeah. So essentially that gives us two parameters instead of one. Okay, great. So so let me provide some more intuition for what these two different quantities mean. So the mutual information is just defined as this combination of the entropies of different regions. And it's in some ways the most natural measure for studying correlations between A1 and A2 if you're given some state. And for pure states, it's a very natural measure because in general, if you have an unentangled pure state, that always means that it's a product state, and the mutual information in that state is 0. So for pure states, the mutual information being non-zero is equivalent to the state being entangled. But this turns out not to be the case for mixed states. So in general, an unentangled mixed state is a separable state of this kind. So it can be some kind of convex combination of density matrices. So some convex combination of different product states between A1 and A2. And you can see that even though there are correlations in this state, these are essentially correlations that you can create just by using some classical communication between someone who's preparing the state in A and someone who's preparing it in A1 and someone who's preparing the state in A2. Because essentially they could have these q different choices. Each of them has q different choices of what state they'll prepare, and maybe one of them has a random number generator. And so they communicate the output of that random number generator to the other person, and it generates the ith state with some probability pi. And so anyway, so you can prepare this state in a purely classical way, and it has no quantum correlations. But if you look at the mutual information in it, then that turns out to be non-zero. So in this sense, the mutual information reflects both classical and quantum correlations in mixed states. So it's not necessarily a good measure of quantum entanglement. But the logarithmic negativity turns out to be a better, more useful quantity from this standpoint. So to define that, suppose we have our density matrix in A, and then we can take a partial transpose in A2. So that just means switching the indices just in the A2 part of the system if you have some tensor product decomposition instead of the whole system. And then in general, this partial transpose is not a well-defined quantum channel. So the matrix that is produced by this partial transpose can in general have some negative eigenvalues. And the logarithmic negativity is essentially a measure of the extent to which it has negative eigenvalues.
So I'm getting lost.
Yeah.
So row A, so A is the union of A1 and A2, right?
Yeah.
And you're taking this transpose only in the block that corresponds to T2. So
A2. Yeah, that's right.
and the T2 in the superscript refers to that.
Yeah.
And the reason that there are 4 indices on your row now, what do these 4 indices refer to? So there's A1 and A2, which...
Yeah. So the 1 and 2 subscripts refer to the basis elements in A1 and A2. So on the left, I have A1, A2, and I'm calling the indices on the right B1 and B2. And then I switch the left.
Got it, thank you.
Yeah.
Sorry, the B1 and B2 are. Oh, they're still.
They're like the
copies.
second index. For
Yeah.
They're the indices in the A2 part. So I left these ones unchanged here, but I switched the ones in A2. Right? Okay, so yeah, and then in general, this operation will lead to some matrix which is not a proper density matrix that has some negative eigenvalues. And you can measure the extent to which it has negative eigenvalues by taking the absolute values of all the eigenvalues and adding them up, and then taking the log. So so essentially the reason for this is that the trace isn't going to be changed by this operation, so all the eigenvalues will still sum to 1. So if all of them were positive, then you would just get log of 1, which would be 0, but if you have some negative eigenvalues, then this is some number which is bigger than 1, and so its log is non-zero. Anyway, so one thing that you can see is that if you consider a separable state like this one, then if you do the partial transpose here, this actually does give you a well-defined density matrix, and all of its eigenvalues will be positive. So for any separable state, you always have 0 negativity. And then if the negativity is non-zero, then you know that you have an entangled state. So in this sense, the logarithmic negativity captures only quantum correlations. I guess there is this issue that you can also actually have some states which are not separable for which the negativity is 0. So that is just something which is not ideal about this quantity, but for our purpose, we'll treat this as a measure of quantum correlations. Okay.
There's no better quantity you can build out of a combination of this logarithmic negativity and the...
You can, no, not from a combination of these. There are many different quantities that people have studied in the QI literature. Like some of these I'll mention, like the entanglement cost and distillable entanglement, and those are better from this perspective, but, or like at least the entanglement cost is better from this perspective, but it's extremely hard to compute.
These are like other simple. You don't need to
Yeah.
optimize and so on, all these things.
Exactly, yeah. Yeah.
Just do a single operation. It's just so simple.
Yeah. Yeah, so it's some kind of compromise. Yeah, and then in principle, what we'll calculate are not directly, is not directly this object, but higher moments of the partially transposed density matrix, so things which look like this. And then we'll try to calculate the negativity from these ZNPTs. So this is similar to using Renyi entropies to calculate the entanglement entropy. So in principle, we can use an analytic continuation prescription to find the negativity from these ZNPTs. So what you do is you take the ZNPTs for even n and analytically continue to n going to 1. And it turns out that that is just equal to this. But the analytic continuation will not turn out to be reliable in the finite temperature calculations that we do. You can use a more reliable method called the resolvent, where you compute this quantity, which involves a power series over all the ZNPTs. And then from this resolvent, you can extract the density of eigenvalues of this partially transposed matrix. And then using that density of eigenvalues, you can plug that into this expression to calculate the negativity. So that's the method that we'll end up having to use in practice because of some issues at finite temperature that I mentioned.
You're now trying to compute this for the equilibrium state, not for equilibrium. I'm confused whether you're working with an equilibrated pure state or some mixed state.
We're not working with a mixed. We're working with an equilibrated pure state on the whole system, but it's a mixed state on this subsystem. Okay.
And it's somehow not possible to just naively, it's like, okay, you just do the transpose and you sum the eigenvalues. Is the problem finding the eigenvalues, or why are we using the resolvent method?
Yeah, to find the, like what you would want to do is just analytically continue this, but you'll find that different, like you'll get some phase diagrams as a function of these parameters, and then different ends will have phase transitions at different points.
No, what I meant is like even more primitively, you gave a formula for the logarithmic negativity.
Yeah.
Just log of some of the
right.
eigenvalues.
So the resolvent is a way of extracting the density of eigenvalues from these moments. So there's, if the only information you have is about these higher moments of rho a T2, then I don't think there's any more direct way of extracting what the eigenvalues are.
So what's the improvement to use a resolvent compared with just using even moments? It seems to be pretty much similar.
Yeah, in principle, they're the same. Sorry?
Similar amount of information, it seems. In terms of this, of course, for this purpose.
Yeah, but what you want to do is like you have some expression like what you would hope is that you get something like this, which is some function of n, which then you take the n going to 1 limit. But it turns out that like this will be, in some cases, you'll find that this is a different function for different n's. So then you can't just analytically continue. But even in those situations, you can always, like this should always be reliable, that you can sum all the different, whatever, like even if it's not a smooth function of n, you can sum whatever you get for all the different n's. And yeah. Okay. So then let me explain a little bit about how, like, what this method is and how we use it to calculate these higher moments. So our starting point will be which I already mentioned earlier, is that we assume that we can identify some rho equilibrium that psi of t resembles macroscopically at late times. And then different choices of this rho equilibrium essentially correspond to different universality classes of equilibrated pure states. So for instance, we could take this to be the canonical ensemble at some temperature, and then different temperatures would specify different universality classes or different forms of the free energy. And then you can also take other choices like the microcanonical ensemble, which we'll do. But anyway, so you make some choice like this. And then you consider just the full expression for the time-evolved quantity ZNPT. So just from its definition, it's expressed in this way in terms of the time evolution operators. So you get some n copies of u in this expression and some n copies of u dagger, and then you get some pattern of traces, which comes from how you define this quantity. So essentially, so you can translate that to a path integral where you have 2n copies. So you have 2n contours in your path integral. So n of these are forward evolutions, which are associated with u. And then n of them are backward evolutions, which are associated with u dagger. And then corresponding to each of these, you get a factor of either e to the is or e to the minus is. And you have some boundary conditions in this path integral. So the initial condition is just determined by the initial state, the actual initial state rho 0. And the final state will be associated with this pattern of traces in this expression. So it tells you how to identify the fields on the different contours. So anyway, so this is some path integral expression. And so now one thing that you can notice about this expression is that this exponent in the path integral will vanish in situations where the field on each forward-going contour is equal to the field on one of these backward-going contours. So the simplest thing that you can do is just set the field on phi 1 equal to phi 1 prime and phi 2 equal to phi 2 prime and so on. But you can also set like phi 1 equal to phi 2 prime and these, like set this one equal to this and so on. So there are many different ways that you can do this. And the number of ways you can do this is just essentially the number of elements in the permutation group. And in all such cases, this exponent vanishes, and you get some stationary contribution which doesn't depend on the time. And then a sort of very heuristic statement you can make is that maybe in chaotic systems at late times, all the other contributions will give some very rapidly fluctuating phases, and they'll all cancel out with each other. So this should be like the right stationary contribution at late times. But if you do this naively, just put this condition into the path integral, you get a divergent answer, which doesn't make sense. So what we did was give a way of sort of doing the same projection onto such configurations in a more systematic way, which involves this state rho equilibrium. Yeah, so that can be seen as like a regularized version of this reasoning. So anyway, so we project onto such contributions, and then we also assume that the effective Hilbert space dimension of the system is large. So for instance, this involves assuming that the partition function is large or something like that. And then, so then you end up with some expression where I haven't explained the notation here, and maybe I can do this at the end or now if people want to. But I think the main things that I want you to notice in this expression are that it's something which involves a sum over different permutations, just like the expression that I showed you on the previous slide. And essentially, these different terms here label states that are associated with different kinds of permutations. So E refers to the identity permutation, and eta refers to the cyclic permutation, which sends n to n minus 1 and n minus 1 to n minus 2 and so on. And so roughly, this is kind of similar to this path integral representation where you have some final state which is determined by the pattern of traces, which is like this final state here. And then you had some initial state associated with rho 0, but after doing this kind of projection, you end up with an expression that depends only on the equilibrium density matrix rho equilibrium, and it doesn't, like the dependence on the initial state rho 0 drops out of this expression.
I have a quick question. So
yeah.
Here you replace the initial state with just the thermal state.
Yeah, well, not quite. So yeah, so it turns out that like it doesn't. One way of seeing that you haven't replaced it with just the thermal state is that if you use this expression, because of this sum over permutations, you'll find that the value of this quantity is not just equal to the value in this equilibrium state. So if you just take the term in this expression, which corresponds to tau being the identity permutation, then you just get the value of ZNPT in the thermal state. But then you also get all of these other terms associated with different permutations, because of which in some regimes the answer will not be the same as in the thermal state.
Can I go back one concern?
Yeah.
This is starting
Yeah.
is not taken anywhere. It's just from our state, it's just arbitrary initial state of 0.
Yeah, so far, this whole part of the discussion didn't depend on the thermal state at all. Yeah. This rho 0 is just assumed to be a pure state. And then, like, eventually in the various inputs that go into driving this expression, I assumed some things about the fact that rho 0 resembles this equilibrium state at late time.
Yeah, by requiring that only phase canceling power contribute, right? So that's the assumption.
Yeah.
That, everything else is a theory.
Yeah.
But still, you're saying it's some dependence on phi 0. But note that this is not equal to.
Yeah, so somehow it.
No. It need not be dependence on phi 0, but it's still different.
It's still different, yeah. It's it's different because it's not just equal to the value in the equilibrium state. And then, so if you do the same thing for the entropy, so you can write down a similar expression for the entropy, and the only difference will be essentially in the boundary condition that you put in the in this final state in the path integral. And then you'll get a similar expression which involves a different final state here and some sum over permutations. But you can show that in that case, that expression will be manifestly consistent with the entanglement entropy in A being equal to that in A bar.
This is a key, right? This procedure is what you claim that something is happening for pure state, despite it's mimicked by thermal state.
Exactly.
Pure state, but it's chaotic. And then this way you don't lose some relevant coherent information for the quantity.
Right. So we're saying that.
That's a claim.
Yeah, it's a claim. Yeah, you can give some kind of self-consistent justifications for it, but it's but it's a proposal.
Right? This is the key.
Yeah.
This is your
Definitely. Yeah. So the key thing is that this expression depends only on rho equilibrium. So it reflects thermalization in that way, but it's also consistent with things like unitarity because of this sum.
This is analogous to the procedure that if your subsystem is bigger than half, you have to take complement.
Exactly. That's exactly what it gives in the case of entropy. Yeah. Okay, great. So, and then the key thing will be that in this expression, as we vary these relative sizes of the different subsystems, the permutation that dominates here will change, and that's essentially what will cause the behavior to deviate from just that in rho equilibrium. And the different dominant permutations will lead to different qualitative forms of ZNPT, and that will give different qualitative forms of the negativity once you use this resolvent prescription to actually calculate it. And we can similarly use this approximation method for the Renyi partition functions. So again, the only difference is in these boundary conditions, and then you can use that to calculate the entanglement entropies for different regions. And then from that, you can find the mutual information.
Can you get the same as replica?
Huh?
Same as replica, you should get.
Same as
replica wormhole.
Yeah. You end up getting replica wormholes in both of these quantities of different kinds. Okay. Great. So so now that was all I wanted to say about the methods. Are there any other questions about that? Okay. So now we can talk about the results. So let's just first start with the simplest case, which is that we take rho equilibrium to be the maximally mixed state. This is just, this can only be done in a finite dimensional system. And this is like considering the infinite temperature case where you have no energy constraints. So the answer in this case, kind of as expected, turns out to coincide with the results that you get from random pure states, which were considered in this paper. And so concretely what we do is we have a parameter lambda, which measures the ratio of the volume of A1 to the volume of A. And then we have C, which measures the ratio of the volume of A to the volume of the full system. Okay, so that gives us our two axes on this phase diagram. And okay, so we get three different phases with these transition lines. So let me explain what they are. So in the case where A is less than half of the system, as we would expect from all of our discussion so far, we find that the mutual information and negativity are both 0 at leading order, so there's no extensive contribution to them. And you find that like a simple picture for why this is happening is that in this case, both A1 and A2 are just entangled entirely with B, and there is no room left for them to be entangled with each other. Okay, so yeah, so this is what you get for the mutual information, and the negativity is just the same. So then you can also consider a similar situation with the subsystems sort of permuted, where A2 is bigger than the combination of A1 and B. And in this case, both A1 and B are just entangled entirely with A2. There's no entanglement between A1 and B. And essentially, the entanglement between A1 and A2 is just proportional to the number of degrees of freedom in A1. So you find that the mutual information is 2 times log dA1, and the negativity is just half of that. Okay, and yeah, and then finally you have this more interesting situation in between where you don't have any of the systems bigger than the combination of the other two, so all 3 are entangled in some non-trivial way, and yeah, and essentially you find that the value of the mutual information or negativity here depends only on the difference in the number of degrees of freedom between A and B, and not like on the specific value of dA1 or dA2 in this regime. And a rough picture for this is that essentially first you use up all the degrees of freedom in A that can be entangled with B, and then whatever is left over is entangled between A1 and A2. Yeah, and then the key thing here is, like in this infinite temperature case, the mutual information and negativity have exactly the same phase diagram, and they're just proportional to each other always. So they're reflecting essentially the same kind of physics, which is also what you would expect intuitively from these bell pair kind of pictures. Okay, so this will not continue to be the case in the finite temperature examples. So now we define our 2 axes in the phase diagram similarly to before. So we just define them in terms of the equilibrium entropies of the different regions instead. And now in terms of these new parameters, the mutual information always has the same phase diagram as in the infinite temperature case. Like the phase transition lines are at the same point, and you just find that the actual values are just quantitatively different, but qualitatively the same. So you get the same picture at finite temperature for mutual information. But the logarithmic negativity turns out to be qualitatively quite different from the infinite temperature case. So here I'm showing the phase diagram for a particular universality class at finite temperature, which I'll explain more later. But yeah, you can see that it's capturing some different physics from the mutual information. And then one particularly striking thing is that you have this region when like below the 0.5 line, where the mutual information is sub-extensive. So it's not exactly 0, but it doesn't have any volume law contribution. But the negativity is some extensive value. Okay? And this should be kind of surprising in the context of what I've told you so far, because I said that mutual information captures both classical and quantum correlations, but negativity captures only quantum correlations. So you would think, based on this, that the quantum correlations can't be extensive in a situation where the mutual information is sub-extensive. But here we seem to be finding a counterexample where there are a lot of quantum correlations which the mutual information is not able to capture. And this seems to be happening sort of universally in these thermalized states.
Can you go back to the definition of your, or calculation of this contour?
Yeah. This one?
Yeah. Where is the information about the temperature? Because you have size 0, but size 0 drops out. So must be something, a regularization or something?
Yeah. There's a regularization which,
kind of
yeah,
right?
it's something I skipped, and I actually have extra slides on it, so I'd be happy to go.
But that's the only place where you can have information about temperature.
Exactly.
Okay.
Yeah. So like I said, here you would have something divergent.
Yeah, so you get that from this expression.
No, absolutely not. Yeah. No, I definitely skipped that, but we can go into that later.
Yeah.
Right, so yeah, so in particular this phase diagram, which I showed you here, this was for a very special kind of, or a sort of strange looking universality class where I take a microcanonical ensemble between A1 and B. So I project onto some small range of energies in the combined A1 and B system. And I just have infinite temperature in A2. And the only reason for doing this and showing you the phase diagram for this case was that somehow the whole calculation of the resolvent simplifies here so that I can actually find what these values are for all C and lambda. Yeah, and then in this calculation, for instance, the only input that I needed besides this choice of ensemble was what form the entropy density takes in the system. So that gives me some form of the density of states, and then I can just do like, I can plug that into the expressions that I had in terms of rho equilibrium, and I get some kind of saddle point integral, which I can do. So anyway, so that's the only input that goes into it. Yeah, but maybe there would be other more natural choices. So two of the other cases where we were able to partially do the calculation in some regimes, but not all, were like a case where you take infinite temperature, sorry, there should be a normalization factor, but you take infinite temperature in A and some finite temperature in B. Or it might be natural to consider a situation where you have a microcanonical ensemble with energy conservation between A1 and A2 and infinite temperature in B. And these were cases where we were able to compute the resolvent using some approximations, kind of not in the full phase diagram, but only in this regime close to C equal to 1/2. But that told us what values we should have in like this non-entangled and this phase. Based on this, you find that in the non-entangled phase, you get 0 at leading order, and then the value above, like in the entangled part, you get a quantity which looks like this, which involves a difference between a sum of the 1/2 entropies in A1 and A2, and the second Renyi entropy of the equilibrium state in B. And the transition just happens where these two quantities become equal. So it happens when the sum of the 1/2 equilibrium entropies of A1 and A2 becomes equal to the second equilibrium Renyi entropy of B. But you can see that the point of showing you this expression is that this has to happen in a situation where, which is before the time at which the equilibrium entropy of A becomes equal to the equilibrium entropy of B. Because we know that the like the 1/2 Renyi entropy is always bigger than the von Neumann entropy, which is always bigger than the second Renyi entropy. And essentially, you can just use these general entropy inequalities and these universal expressions to show that more generally, you would have situations where the mutual information will be subextensive in this regime, and then you have some region in your parameter space where the negativity is extensive.
What's the choice you made in that article?
Sorry?
What's the choice you made?
In this picture?
Yeah.
In this picture, I made this kind of weird choice where I have the microcanonical ensemble in A1 and B and infinite temperature in A2. Yeah, and I did this just because it simplifies the calculations. Yeah, but then this main sort of striking result about negativity being much bigger than mutual information turns out to also be true in other universality classes. But we don't know how to find the analogs of these parts of the phase diagrams, which I'll comment on more later. Okay, any questions at this point? Okay, so yeah, so this is a pretty surprising result that the negativity is much bigger than the mutual information. And I think, yeah, we would like to understand this a lot better, but one way in which we can interpret it or understand one consequence of it is in terms of two operational measures called entanglement cost and distillable entanglement. So let me first define what these are. So to define the entanglement cost, suppose you have a hypothetical situation where you want to prepare your state rho A1, A2, and you want to do this by starting with some n EPR pairs between A1 and A2. And then you want to act with only local operations between A1 and A2 and some classical communication between them. If you want to do this, then you'll need some minimum number n. And essentially, this minimum n is equal to the entanglement cost. Okay? And then you can define the distillable entanglement in a similar way by considering the reverse process, where you start with your state rho, and you want to act only with LOCC operations and get some number of EPR pairs out of that process. So if you want to do that, then there'll be some maximum number m that you can get out. And this m will be your distillable entanglement. Okay, so for a pure state, it turns out that both of these quantities are just equal to the entanglement entropy of either of the subsystems. And this is also why the entanglement entropy or the mutual information is a very natural quantity for pure states. But for mixed states, in general, the entanglement cost can be much bigger, in general, it's bigger than the distillable entanglement. And neither of these has to be equal to the entanglement entropy or the mutual information or the negativity. But what is kind of useful, and then the other thing is, like, these are very natural measures to consider, but they're very hard to compute even if you have some few qubit systems. So definitely in a many-body system, I don't think there are any examples where people have calculated them. But what you can do is relate them to these more computable measures like negativity and mutual information through some upper and lower bounds. So in particular, there's a sort of variant of this standard entanglement cost you can define, which is lower bounded by the logarithmic negativity. And you can also show that the mutual information gives an upper bound on the standard distillable entanglement. Okay, so then by using these inequalities and by using some further inequalities between the different kinds of entanglement costs, you can show that if you have a situation where the negativity is much bigger than the mutual information, then a certain kind of entanglement cost has to be much bigger than the corresponding distillable entanglement. So that is one sort of physical consequence of the relation between these quantities, that in this regime you have a state, like if you just consider the reduced state on A, then its preparation from EPR pairs would be a highly irreversible process. But that's just one consequence, and it would be nice to understand more about the structure of the state which leads to negativity much bigger than mutual information, and why this arises at finite temperature. So far everything that we said was about general quantum many-body systems. But now we can try to apply what we've learned from these systems to black holes. So like I said before, we can consider our setup with A1, A2, and B to now be such that these two parts that we're looking at the entanglement between are two parts of the radiation, and B is the remaining black hole. So then, essentially during the evaporation process, this whole R system becomes bigger, and that can be seen as sort of going upwards in both of these diagrams to find the corresponding values of these quantities. So then, because of this universal form of the phase diagram of the mutual information, we find that the mutual information between R1 and R2 will become extensive at the page time, which is just defined by the time when the equilibrium entropy of the radiation becomes equal to the equilibrium entropy of the black hole. And based on this, it's generally believed that the entanglement within the radiation starts to grow at the page time. But we now find that at finite temperature, the logarithmic negativity starts increasing at an earlier time scale TB, which is the time when the 1/2 Renyi entropy of the radiation is equal to the 2nd Renyi entropy of the black hole. Okay, and because of the inequalities that I mentioned before between the different Renyi entropies, this always has to be earlier than the standard page time. So this is telling us that somehow there is some kind of entanglement within the radiation well before the page time, but it's this weird kind of bound entanglement which can't be distilled into EPR pairs. So just to summarize, so if you look at the mutual information at, if you first consider the infinite temperature case, like Page's calculation with random pure states, then you find that both the mutual information and the negativity start increasing at the same time scale, which is the usual page time. But if you look at finite temperature, then the mutual information still starts increasing at the page time, but the negativity starts increasing at this macroscopically earlier time scale TB. And in this regime, you have bound entanglement. Okay, so you can see this either as a prediction about black holes from general properties of chaotic quantum many-body systems, or you can make the connection a little bit more direct in like using some Euclidean gravity prescriptions. So I showed you this expression for Z and PT, which involved the sum over permutations. And I didn't explain in detail what this was, but essentially it involves taking, like this will end up involving some n copies of rho equilibrium connected in the different copies by some, and they would be connected in the different copies in some way which is determined by this permutation. So essentially, because, like for instance, if you took this to be e to the minus beta h, you can see each of those factors as some Euclidean path integral. You can interpret each term in this expression as a Euclidean path integral on n copies of the system, and it would have some, this Euclidean path integral has some boundary conditions which are determined by the permutation. And then you can see if you have a holographic setup, like a model by Pennington, Schenker, Stanford, and Yang, then these kinds of Euclidean path integrals can be seen as boundary path integrals, and you can equate each of them with a bulk path integral. And it'll turn out that in all cases except for the identity permutation, these bulk path integrals will have replica wormholes. So in particular, the dominant contributions in these phases where you have some entanglement between the two parts of the radiation, both of these phases are obtained in the Euclidean gravity picture by two different kinds of replica wormholes. So in this particular model, it turns out that, so there we can do the mapping very precisely. We can give some, we can show that their calculations correspond to a particular choice of this rho equilibrium. So you can see what answer you get from that for these phase transitions. But there somehow, because of the very special structure of the density of states in JT gravity, you find that there isn't a macroscopic difference between the second equilibrium Renyi entropy and the just the von Neumann equilibrium von Neumann equilibrium entropy. Because of that, you find that there's actually a very small difference between these two. Like in this phase diagram, for this model, you would find that essentially this earlier transition line for the negativity, the difference between that and the transition line for the mutual information is just suppressed in the volume of the system. But but this should be like a special feature of two-dimensional gravity. And for higher dimensional black holes, from what we know about the form of the density of states, we should find that the second equilibrium Renyi entropy and the von Neumann equilibrium Renyi entropy have some difference which is proportional to the volume. So this should be some genuinely macroscopically earlier time scale. So anyway, so you can give some precise prescriptions for what these different contributions correspond to in the Euclidean gravity prescription. But I think what would be really interesting is to see if, to see if this kind of entanglement before the page time can also be seen from some Lorentzian gravity calculation. Like for instance, if we had some sort of Lorentzian holographic dual of the logarithmic negativity, and we could see that it has something like an island or something which leads to entanglement before the page time. So that would be an interesting question for future work. So maybe I'll explain some of the more technical things about why we needed to do how much time do we?
Go 5 more minutes or something.
5 more minutes, yeah. Okay. Okay, then maybe I'll very quickly do this slightly technical discussion. So in the infinite temperature, so recall that what we actually calculated were more like these Renyi mutual informations, and Renyi versions of the logarithmic negativity. And in the infinite temperature case, everything ends up being simple because if you look at these different ZNPTs for different n, all of the phase diagrams just coincide, and they're all the same as that diagram that I showed you earlier. But then if you look at finite temperature, you find that you get a distinct phase diagram for all the different n's for ZNPT. So for instance, if you look at this example for which I showed you the logarithmic negativity phase diagram before, if you looked at, if you looked at the phase diagrams for ZNPT, so these are labeled by R because they're also related to quantities called Renyi negativities. But anyway, these 3 different lines correspond to 3 different even values of n for ZNPT, and they have phase transitions at different points. So this means that if I consider a point here, for instance, I don't know what, which expression for ZNPT I should be analytically continuing and what phase I'm in. Yeah, but then when you do the whole resolvent calculation, you find that the phase transition lines are just, it's not like the ES phase here is the intersection of all of the ES phases for the ZNPTs. It's just something different. And another interesting thing that you find is that for each of these ZNPTs, you have only 3 phases, which are like the phases at infinite temperature. But at finite temperature, you also get these 2 new phases, which don't correspond to analytic continuation of the ZNPTs. So yeah, so that's a slightly technical point, but it's kind of interesting that if you look at finite temperature and these quantities, then you have to go beyond analytic continuation. Okay. Okay, so yeah, so maybe in the last few minutes, I can talk about I can switch gears a little bit and talk about a different set of results about information transfer. So here I want to think about a question where I have a secret diary, I write something in it and throw it into a black hole. But then later, for some reason, I want to retrieve its contents by collecting the radiation of the black hole. And my hope could be that as I collect more and more of the radiation, then eventually the initial state of the diary can be recovered from it. So this whole process of throwing the diary in and losing access to the black hole path can be seen as a quantum channel from the Hilbert space of the diary to the Hilbert space of the radiation. I'm assuming that the initial state of the black hole is some fixed state. And the attempt to retrieve the information that I put in the diary is essentially the attempt to reverse this quantum channel and go back from the Hilbert space of the radiation to the Hilbert space of the diary. So given any quantum channel, I can always write down a recovery channel which attempts to reverse it, which is something called the PETS map. So this is, yeah, so maybe you don't need to look at this expression too much, but it involves some reference state in the diary Hilbert space, and it involves this original quantum channel. And anyway, I can always write this down. But in situations where it's not possible to recover the information from the radiation, I should find that it gives me some bad answer, which is not the actual initial state of the diary. So to measure this, I can look at what output I get from the PETS map and look at its fidelity with the actual initial state of the diary. And in particular, if this fidelity is small, then I know that I have some small likelihood of being able to recover the information through this method. And if the fidelity is large, if the fidelity is close to 1, then I know that I have almost perfect information recovery. So yeah, so again, to calculate this quantity, we can use the same trick as before. So you can kind of see from this definition of n and how many n's appear here that somehow you see if you change this -1/2 to some general integer like m, then this will give you again some expression which involves some number of copies of u and some number of copies of u dagger. And you can again write it as a transition amplitude and do the same trick as before. So this kind of replica trick was first used in this paper, and we can just consider a finite temperature version of it by using the equilibrium approximation. Okay, so now let me just summarize the results from that. So you can consider 2 kinds of cases. You can consider that you have a small diary whose size doesn't scale with the total volume of the system. or you can have a large diary whose size does scale with the total volume. And you can consider infinite temperature, which is more like the standard story that we know well, and you can also consider finite temperature. So let me just summarize what happens. So in all of these cases, initially when there is a small amount of radiation, you get some exponentially small value of this fidelity. So that's telling you that you can't really recover what your state is. And eventually it saturates to a value close to 1. So you know that if you have a sufficient amount of the radiation, then you can recover the information. But the way that it evolves from these two extremes is kind of interesting. So let's just first consider the infinite temperature case, where the usual story from Hayden and Preskel is, so this fidelity turns out to exactly reflect what we normally expect from Hayden and Preskel. So before the page time, you find that the fidelity is quite bad. You can't recover the information. And then very quickly after the page time, you find that you can recover the information of the diary almost perfectly well. So that's the case for a small diary. If you have a large diary, then it turns out that the fidelity first starts to increase at the page time from its exponentially small value. So this can be seen as a logarithmic scale. And then there's some exponential improvement until eventually it saturates to 1 at some time scale TP2, which is after the page time, which is defined in this way as the time when the equilibrium Renyi entropy of the radiation, the equilibrium entropy of the radiation becomes equal to the equilibrium entropy of the black hole plus the log of the dimension of the diary. So this time scale was identified in this paper on alpha bits by Hayden and Pennington. Anyway, so one thing that is nice but not entirely unexpected is that not only do you see that you can perfectly recover the information at this time scale, but you can see a sort of gradual improvement starting at the page time by looking at this fidelity quantity. But now if you consider the finite temperature case, you find that if you have the case of a small diary, then you see the same thing as at infinite temperature, where initially the fidelity is bad, and then right at the page time, it very quickly becomes 1. But if you consider a large diary, then something interesting happens where you see that the point at which it eventually becomes 1 is, again, this TP2 timescale. But
small or large compared to what?
Sorry, it becomes 1.
A small or large diary?
The orange one is the large diary.
No, what I'm asking is what's your definition of small or large?
Oh, so I'm just saying whether log dd is proportional to the volume of the full system or not. Yeah, because essentially if you have just like an order 1 number of qubits in the diary, then there is no reason why there would be a long time scale over which the fidelity would gradually improve. And indeed it comes out at the usual page time, even at finite temperature if you have a small diary. But if you have a large diary, then you find that this exponential improvement from the initial very small value will start not at the page time, but at this same earlier time scale TB that we identified from the negativity calculations. But this just comes out of a totally different calculation in this case. So that was the really striking thing that looking at the Hayden-Preskel experiment gives you a more operational interpretation of this TB timescale.
Sure, just a quick question. So
Yeah.
at the page time, is that still sort of like exponentially small? Because by your plot, it kind of looks like it, right? Like that.
Yeah.
It increased, but it's still exponentially small.
Yeah, that's right.
Okay.
Good. Okay. So again, one interesting question to pursue in the future from this would be to see if somehow entanglement wedge reconstruction tells you more about this situation where like the fidelity of reconstruction is close to 1. So it would be nice if we could see some version of this quantity which captures the gradual improvement of the likelihood of recovering information, and if we could find some holographic dual for it. And then we would potentially be able to see things like the fact that at finite temperature, this fidelity starts growing at this earlier time scale. Another thing that I think is kind of interesting is, so there is a known lower bound on the fidelity of a certain recovery map in terms of the relative entropies like the change in relative entropies under applying the quantum channel. So it's just some inequality which has this form. And this is not necessarily, this is something called the twirled Petz map, which is in principle slightly better than the Petz map. But anyway, you can also just use the equilibrium approximation to calculate this difference in relative entropies, because again, this is some quantity which has a replica trick, and you can do this. But if you were to make the same plot for this quantity, you would find that it's not sensitive to this time scale TB, and it only starts growing at the page time in the setup. So somehow, like the negativity between two parts of the radiation does start growing at TB, but the usual known lower bound from relative entropies in quantum information theory doesn't. So it would be interesting to see if purely from an information theoretic viewpoint, there's some kind of relation between these two quantities, even outside of this black hole context. Yeah, or there's some reason why this is happening that's not just coincidence. Okay. Yeah, so I guess that's all I wanted to say. To summarize, we developed a general method for expressing information theoretic measures in thermalized pure states in terms of equilibrium quantities, and applied this to logarithmic negativity at finite temperature. And from this, we found some surprising features of thermalized states. In particular, we found that at finite temperature, mutual information and negativity reflect very different physics, and the negativity can be much bigger than mutual information, which is kind of surprising. And in evaporating black holes, this led us to identify an earlier than expected timescale TB when the entanglement within the radiation starts to grow. And this turns out to also have some operational interpretation in terms of information recovery. Yeah, and I have some further questions, but I think I mentioned most of them already. So I guess one thing that I didn't mention maybe is that there were these phases which you can't get by analytic continuation that I mentioned in this special universality class. So it would be interesting to see if there are also phases like this in the other universality classes, which we don't have access to from our calculation in the approximate regime. But if they exist more generally, then it's not clear how you would see them from a gravity calculation, just because we usually use analytic continuation of geometries in gravity. So yeah, that's everything. Thank you.
So any questions for?
Yeah.
I have two related questions. The one is that if you take some universal class that it's a microcanonical ensemble throughout A1, A2, and B,
Yeah.
then would you be able to get the phenomenon that radiation entanglement occurs earlier than the page time? I guess it's not, but
That case turned out to be the most difficult to calculate out of all the different cases that we considered. Like somehow, like in that case, it's even hard to calculate these ZNPT quantities.
so you don't know.
Yeah, we don't know.
Yeah,
Yeah.
I guess it's no. I think it's a totally random thing is the fastest compared with the all finite temperature throughout the space, infinite temperature. But anyway, you don't know. Okay.
Yeah, we don't.
Yeah.
Wait, sorry. What is your intuition for why it should?
No, because in a case of page calculation, everything is like infinite temperature, so it's just really mixed up.
Yeah.
So that's probably the fastest compared with the lower temperature of the entire thing. Like a microcanonical ensemble, entire temperature is not infinity, but it's still microcanonical.
Right.
So that's guess. But
So it should. You think it should be just as totally mixed?
Probably. Yeah, it's just slower if any difference. But
Okay.
if that's the case, because of that's kind of naive. If it's different, that's very interesting. But because that's a naive expectation, my worry. This is the second question. My worry is that what we did is like you put like B, A2 or whatever to be kind of microcanonical. For example, in one of the cases, you got this phenomenon.
Right.
And A1 is infinite temperature.
Right.
That means that you kind of extracted energy from the black hole because this is infinite temperature. It's higher energy than you expected from that case.
Right.
So you just artificially extracted energy from the black hole. So something it doesn't happen in a thermal. That's why you get the information recovery earlier. That's the worry.
Okay,
You know,
interesting.
that's something it doesn't happen in physics. You should
Right.
let it go, and then it never happens. But you kind of like set up by setup. You
Right,
just
right.
right. I mean, you move the energy from black hole to the bar by hand faster
Yeah.
than that. That might be the origin of all this phenomenon. That's a
That's
worry.
interesting. Yeah. I guess, so, yeah, the other cases that we considered were so this one, which is maybe kind of similar to what you're saying, so you take the radiation to be at infinite temperature.
So always you get something.
But this one is not. But this one is not really, like here where you have energy conservation between A1 and A2 at some finite energy.
You get that as well?
Yeah,
Okay,
yeah.
that's good to know. That may be a good counter argument.
Yeah.
That way. Yeah, I think so. But yeah, anyway, okay.
Yeah, I guess the logic that we had for taking different equilibrium density matrices and radiation and black hole is that eventually the radiation just becomes separated from the black hole, so it doesn't have to come to the same equilibrium.
Even in that case, you get faster than audio advantage time to get.
Even in this case, yeah, we do, yeah.
Okay, that's
Yeah, so we get the same time scale in this case. Yeah.
Any other questions? Not, let's thank Shreya again.